Hi students, good morning. I am Kishore, working as a physics lecturer in Vigyan College. So now we will see the chapter Mechanical Properties of Solids. So let us see some problems that are given in previous JEE mains exam. See the next problem. The pressure that has to be applied to the ends of the steel wire of length 10 cm to keep its length constant when its temperature is raised by 100 degrees centigrade is, and for steel the Young's modulus is 2 into 10 power 11 Newton per meter square, and the coefficient of thermal expansion is 1.1 into 10 power minus 5 per Kelvin. So here we have to find the pressure. We have to find the pressure here, and the length of the wire is given as, length is equal to L, which is given as 10 centimeter. And here the length remains constant, so temperature rises by delta T. So rise in temperature is so let us consider it as T, which is given as 100 degrees centigrade, and the Young's modulus is given as Y is given as 2 into 10 power 11 Newton per meter square, whereas the coefficient of linear expansion, which is given by alpha, is given as 1.1 into 10 power minus 5 per Kelvin. So we know the pressure is nothing but stress. Both have same units as well as same dimension formula. So you have to find the stress, and we know the Young's modulus is given as stress by strain. So from this, the stress becomes equal to Y into strain. So here the Young's modulus is given, and how to find the strain, and strain is nothing but delta L by L, with the change in length by original length, and we know the change in length is nothing but alpha L into change in temperature divided by L. So here length is constant, so L get cancelled, so you get the strain as alpha into T. So the pressure becomes equal to stress, which is nothing but Y into strain is nothing but alpha into T. So here the Young's modulus is given as 2 into 10 power 11, and alpha is given as 1.1 into 10 power minus 5, and the temperature is given as 100. On simplifying this, we get this as 2.2 into 10 power 8 pascals. So this is the value of pressure. So we get the pressure as 2.2 into 10 power 8 pascal. So the next problem, a copper wire of length 1 meter and a steel wire of length 0.5 meter having equal cross-sectional area are joined end to end. The composite wire is stretched by a certain load which stretches the copper wire by 1 millimeter, and if the Young's modulus of the copper and steel are respectively 1 into 10 power 11 Newton per meter square and 2 into 10 power 11 Newton per meter square, the total elongation of the composite wire is. Here in this problem, the copper wire length is given as, so let us consider the length of the copper as L, C, which is given as 1 meter, and a steel wire of length, so length of steel wire is given as 0.5 meter having equal area. That means the area of copper is equal to area of steel wire, and the wire stretches by a certain load which stretches the copper wire by 1 millimeter. So here elongation of the copper wire is nothing but 1 millimeter, and if the Young's modulus of the copper and steel are given as, so Young's modulus of the copper is equal to 1 into 10 power 11 Newton per meter square, whereas the Young's modulus of the steel wire is given as 2 into 10 power 11 Newton per meter square, and we are asked to find the total extension or total elongation. We have to find the total extension. So here the formula is given nothing but Young's modulus, which is given by FL by A E, and here area is same, so area is given as A is equal to FL by EY. So here area of the copper is same as area of the steel. So here in this problem the area is given as same. So area of copper is must be equal to area of steel. So you get force of copper into length of copper divided by elongation of copper into Young's modulus of copper must be equal to for the steel wire. Here they are stretched by same load, so that means the force becomes equal in both the cases. So length of copper is given as 1 and elongation of the copper is given as 1 millimeter, which is nothing but 1 into 10 power minus 3 meter into Young's modulus of copper is given as 1 into 10 power 11. That should be equal to the length of steel is given as 0.5 meter divided by, you have to find the elongation of the steel, let us consider it as ES, and Young's modulus is nothing but 2 into 10 power 11. So from this you have to find the elongation of the steel wire, so which is nothing but elongation of the steel is equal to 10 power minus 3 into 10 power 11 into 0.5 divided by 2 into 10 power 11. So 10 power 11 get cancelled. From this you can calculate the elongation of the steel wire. So we get the elongation of the steel wire as 0.25 millimeter. So the total elongation is nothing but our total extension is equal to elongation of copper plus elongation of steel, which is nothing but 1 plus 0.25. So you get this as 1.25 millimeter. So this is the total elongation of the composite wire. So the next problem, the uniform wire Young's modulus is given as 2 into 10 power 11 Newton per meter square is subjected to longitudinal tensile stress of 5 into 10 power 7 Newton per meter square. If the overall volume change in the wire is 0.02%, the fractional decrease in the radius of the wire is close to. So here the Young's modulus of the wire is given as Young's modulus Y of the wire is given as 2 into 10 power 11 Newton per meter square, and the stress is given as 5 into 10 power 7 Newton per meter square, and the change in the volume is given as delta V is equal to 0.02%, and we are asked to find the fraction decrease in radius, that is delta R by R have to find. So the Young's modulus is given by Y is equal to stress by strain. This is nothing but stress by strain is nothing but delta L by L. So from this we get delta L by L is equal to stress by Y. So here the stress is given as 5 into 10 power 7 divided by Y is given as 2 into 10 power 11. So on simplifying this we get delta L by L as delta L by L is equal to 2.5 into 10 power minus 4. And now volume is nothing but pi r square L. So delta V by V is nothing but pi into delta r square L by pi r square L. So it is nothing but r square into delta L plus L into 2R delta R divided by R square L. So from this we get this as, let us take L as capital, that becomes delta L by L plus two into delta R by R. So this is delta V by V. From this, 2 into delta R by R is equal to delta V by V minus delta L by L. This is nothing but delta V is given as, delta V by V is given as 0.02 divided by 100 minus, and delta L by L we get as 2.5 into 10 power minus 4. So on simplification this we get this as delta R by R is equal to minus 0.25 into 10 power minus 4. See next problem. A steel wire can sustain 100 kg weight without breaking. If the wire is cut into two equal parts, each part can sustain a weight of. So the stress or breaking stress is given as force by area. So here the stress is constant, so the force is proportion to area. So if force depends on area, so the load does not depend on length of the wire. So the wire is cut into two equal parts, so each wire can sustain a 100 kg weight because load does not depend on length of the wire. The next problem. A structured steel rod has a radius of 10 mm and length of 1 meter. A 100 kN force stretches it along its length. The Young's modulus is steel is 2 into 10 power 11 Newton per meter square. The percentage strain is about. So the rod has a radius of 10 mm. So the radius of the wire is given as 10 mm and length is given as L is equal to 1 meter and the force F is given as 100 kilonewton. This is nothing but 100 into 10 cube Newton. So convert radius also into meters, so you get 10 into 10 power minus 3 meter. So the Young's modulus, let us imagine Y is given as Y is equal to 2 into 10 power 11 Newton per meter square. We are asked to find the percentage strain. So the Young's modulus is given as Y is equal to stress by strain. So from this we get the strain as stress by Y, and we know stress is nothing but force by area. So the strain becomes equal to, stress is nothing but force by area, so it is F by Ay. So here F is given as 100 into 10 cube, whereas here is nothing but pi r square. Pi into r square is nothing but 10 power minus 2 whole square into the Young's modulus is given as 2 into 10 power 11. Whereas the percentage strain is nothing but is 10 power 6 divided by pi into 10 power minus 4 into 2 into 10 power 11 into 100. This is the percentage of strain. So on simplifying, we get the percentage of strain as 0.16%. See the next problem. Two steel wires having the same length are suspended from a ceiling under same load. The ratio of their energy stored per unit volume is 1:4. The ratio of their diameter is. So here the two steel wires, that means both are made up of same material. So for both the wires, Y is same, that is both are made up of same material. So Young's modulus is same. Having same length, so length is also same for the two wires. Are under same load, so F is also same for the two wires. And the ratio of the strain energy, if we consider the energy as U1 and U2, the strain energy ratio is given as, so U1 by U2 is given as 1/4, and we asked to find the ratio of diameters. So we have to find the ratio of diameters. And we know the strain energy per unit volume given by half into stress into strain. This is the formula for strain energy per unit volume, half into stress into strain. Now here, so F is same, Young's modulus is same, so length is same. So that's why let us convert in strain into in terms of stress. So Y is given as stress by strain. So strain becomes equal to stress by Y. So stress is nothing but force by area, so it is nothing but F by AY. So now the strain energy per unit volume becomes equal to half into stress is nothing but force by area divided by strain is nothing but F by AY. So from this it becomes F square by 2AY. So A is nothing but area, 2A square Y. So here A is nothing but area, which is nothing but pi r square. So this is equal to F square by 2. Area is nothing but pi r square all square into Y, and this is equal to F square by, so we are asked to find diameter, which is nothing but D by 2 whole square into Y. So this becomes F square by 2 pi square, so this is D square by 4 whole square. So it becomes D power 4 divided by, so 2 power 4 into 1. So from this relation, if we consider the strain energy per unit volume as U, then we get U, the relation between strain energy per unit volume and diameter is, so it is inversely proportional to 4th power of diameter. So from this we can write U1 by U2 is equal to D2 by T1 power 4, and U1 by U2 is given as 1/4. So 1/4 is equal to D2 by D1 power 4. So we get D1 by D2 is equal to 4 power 1/4. See the next problem. In materials like aluminum and copper, the correct order of magnitude of various elastic moduli is, we have to find the order. And we know the Poisson's ratio is given by Poisson ratio, nothing but lateral strain by longitudinal strain. So this is denoted by sigma, and for copper the sigma is approximately about 0.33, and we know y is equal to 3k into 1 minus 2 sigma. 9 by y is equal to 1 by k plus 3 by eta. Y is equal to 2n into 1 plus sigma. Here the order is eta is less than, y is less than k. That is, the shear modulus is less than, Young's modulus is less than bulk modulus. So the answer is C. So the next problem, you can see the stress and y is the Young's modulus of the material of the wire. The energy stored in the wire per unit volume is. So the stress is given as S, and the Young's modulus is given as is equal to Y. The energy stored in the wire per unit volume is energy stored per unit volume. So the expression is given as energy stored per unit volume is equal to half into stress into strain. But here we are asked to in terms of stress. So we know y is equal to stress by strain. From this, strain is given as stress by y. Then the energy stored per unit volume is equal to half into stress, and instead of stress we are strain we are writing stress by y. So it becomes, the stress is given as S, so it is S square by 2y. So this is energy stored per unit volume. The next problem, a wire fixed at the upper end stretches by length L by applying a force F. The work done in stretching is. So here the stretching is given as, stretching is nothing but increase in length, which is given as L, whereas the force is given as F. We have to find the work done. And we know the work done stretching the wire is stored in the form of potential energy. So the work done is equal to change in potential energy, which is given by half into stress into strain into volume. And we know stress is nothing but force by area, and strain is nothing but delta L by L, and volume can be written as area into length. So half into stress is nothing but force by area, and strain is nothing but delta L by L, but here delta L stretching is given as L, into volume is nothing but area into length. So area and length get cancelled, so we get this as half into F into delta L, but here the delta L is given as L. So this is the formula for work done. So W is equal to half into F into L. This is equal to FL by 2. This is the work done in stretching the wire is equal to FL by 2.